Welcome to the class. Dear students, today we are going to see Perkin condensation. In Perkin condensation, we will first which compound shows this reaction. Then we will see what is the product of the reaction. We will see the reaction itself. We will discuss 3 points on the reaction. Then we will go to mechanism, which consists of 5 steps. And lastly, we will discuss the significance of the reaction. So let us start Perkin condensation. So Perkin condensation, it is shown by aromatic aldehydes. Only aromatic aldehyde will show Perkin condensation. So what is the reaction? Aromatic aldehyde, it reacts with anhydride of an aliphatic acid. Anhydride of an aliphatic acid in the presence of sodium salt of the same acid. In the presence of sodium salt of the same acid as catalyst to produce or to yield alpha beta. This is alpha, this is beta. Alpha with respect to COH. Alpha beta unsaturated aromatic acid. Alpha beta unsaturated aromatic acid. Okay, no need to signify where is the COH group or where is the phenyl group, because it is understood that COH group will be attached to alpha carbon atom and aromatic acid will be attached to beta carbon atom. So simply you can say alpha beta unsaturated aromatic acid. Okay, so now this compound is also called as this is C. Look at this. This is actually acrylic acid. This is acrylic acid. So this would be what? What would be this? This would be beta phenyl acrylic acid. This is beta carbon atom, beta phenyl acrylic acid or beta aryl acrylic acid. So it is also called as beta aryl acrylic acid or beta phenyl acrylic acid. Okay, and this is the simplest of all alpha beta unsaturated aromatic acid. Simplest. All other alpha beta unsaturated aromatic acids are derivatives of this. So this is the simplest of all, because we have used the simplest of all aromatic aldehyde and the simplest of all aliphatic anhydride. So this is the simplest of all alpha beta unsaturated aromatic acid. So this common name for this is cinnamic acid. Okay, so all other, that is, if you are using higher aldehydes or higher aliphatic anhydride, then you will get derivatives of cinnamic acid. Derivatives of cinnamic acid. So this is the reaction. What did we discuss till now? First of all, it is shown by aromatic aldehyde. Second, the product is alpha beta unsaturated aromatic acid. The third thing is, let us go to the reaction. The third thing that we have discussed is aromatic aldehyde, when it reacts with anhydride of an aliphatic acid in the presence of sodium salt of the same acid as catalyst, then you get alpha beta unsaturated aromatic acid. It is also called as beta aryl acrylic acid, and the common name of this, which is the simplest of all alpha beta unsaturated aromatic acid, is called as cinnamic acid. So if you are using higher, you will get derivatives of cinnamic acids. That is what we have discussed. So this is the reaction, dear students. Now let us discuss 3 points on this reaction. First of all, it is a condensation reaction. What is it? A condensation reaction. What is a condensation reaction? Condensation reactions are addition reaction with the elimination of small molecule. Small molecule may be of water, it may be of methanol, ethanol or acetic acid. Okay. So here we are seeing it's a condensation reaction. Reactants are adding up to each other, right? Aromatic aldehyde and acetic anhydride add up to form an adduct with the evolution of very small molecule or simple molecule of ethanol. So therefore, it fits the definition of a condensation reaction. Therefore, it is a condensation reaction. The second point is that this is the base catalyst. Okay, it is acting as base catalyst. How it is acting as a basic catalyst? Let us see. We know that CH3, this is CH3, CO minus Na plus, right? It won't exist as such. It would exist as CH3CO minus and Na plus. According to Lewis base, what is a Lewis base? Lewis base is a substance that can donate a pair of electrons. It can donate a pair of electrons. So here we are seeing that it is a donator of a pair of electron. What it does actually is it knocks out a hydrogen from this. From acetic anhydride, it knocks out a hydrogen. So if it knocks out a hydrogen, of course it becomes CH3COOH, no doubt. But here it would become anion of acetic anhydride, right? A negative charge will come here. When H plus was taken, its pair of electron remained here and a negative charge came here. So this would become an anion of acetic anhydride. Look at this molecule. There is a rift between carbon and oxygen. They are of opposite nature. This becomes negative and this becomes positive. You know that. So this carbon is positive, positively charged. Now what happens is that this anion gets attached to this carbon. Anion gets attached to this carbon. So this is what makes it similar to aldol condensation. If you don't know what is aldol condensation, please refer my video aldol condensation, wherein I have discussed what aldol condensation is. So here what I said is this would become negative, and this negative part, negative and acetic anhydride, the anion of acetic anhydride would come and attach to this positively charged carbonyl carbon. Okay, so that is what makes it similar or analogous to aldol condensation. Okay, and as I said, this is the basic catalyst. Base, I have shown how it is a base and how it knocks out H plus. Now a catalyst is something that is required in very small quantity. It is required in very small quantity, and the second is it should be restored back. It should not participate in the reaction. It should restore itself back. So here suppose we are using this in small quantities, CH3CO minus we will get, correct? We will get acetate ion that would knock out a hydrogen and that would yield an anion of acetic anhydride. Okay, that would make it CH3COOH, correct? If H plus is taken by this, it will become acetic acid. Now this also, it will become CH3CO minus, right? It is a weak acid, so it also will become CH3CO minus and H plus, correct? So this also we are getting acetate ion spontaneously. No need of any catalyst, we are getting acetate ion spontaneously in the reaction. We are getting acetate ion spontaneously. How it is? Because our catalyst is getting dissociated. The dissociated acetate ion now knocks out the hydrogen from here to become acetic acid. That acetic acid dissociates again to become acetate ion. So we need a very small quantity of it just to start the reaction. So catalyst is required in small quantity, that is proved. Now this acetate ion, no, it can again combine with Na plus and it can again become CH3COO minus Na plus. Am I right? Some of it may combine, right? If not all, some of it may combine with Na plus and it would again become CH3CO minus Na plus. That proves the second point, that is, it is restored. The catalyst does not take part in the reaction, it is restored. So these are the points that I wanted to state before starting or before stating the mechanism to you. I hope it is clear. So what are the points? Perkin condensation. Why it is a Perkin condensation we have discussed, because it involves addition with the elimination of small molecule of acetic acid. The second thing that we have discussed is this acts as a base catalyst. Why it is basic? We have shown you it is a Lewis base and it knocks out H plus. Okay, when it knocks out H plus, this becomes negative and this negative part attaches to carbonyl carbon. This makes it similar to aldol condensation. We have discussed that. And the catalyst has to be used in small amount. It has to be restored back in the reaction. And why and how we have proved it here. Correct? This a small amount, it would become CH3COH. The CH3COH would again become acetate ion. So acetate ion is generated spontaneously. Okay, so small amount is required and some of it may combine with Na plus to give sodium acetate. So it is restored back. I hope it is clear. Let us now go to mechanism. So what is the mechanism of this reaction? Mechanism Mechanism is nucleophilic addition reaction. Nucleophilic addition reaction. Nucleophilic addition reaction is the mechanism. Nucleophilic addition reaction. What is this? Let us see the step 1. Step number 1. Just a minute. Let me take a new marker. Okay. Pardon me and thank you for waiting. Step number 1. Formation of carbon anion. Formation of carbon anion. Let us see what happens. Okay. Formation of carbon anion. Let us see what happens. Nucleophilic addition reaction is the mechanism. There are 5 steps in the mechanism. The first step is formation of carbon anion. So we have used the catalyst CH3COO-Na, right? Sodium acetate. Of course, it is dissociating, and on dissociation we get acetate ion. Is there any doubt on that? No. Right? And we have acetic anhydride. I am going to write acetic anhydride like this. Right? So I am going to rub this. I am going to write it CH2 and H. One and the same thing, right? It's a very strong base. It knocks out a H from here. That will leave the electron pair and this would become negative. So what you get? CH3COOH, no doubt, acetic acid. A small molecule is evolved in the first step itself. And the second thing that you get is, yes, you guessed it right, a carbon anion, or you can say an anion of acetic anhydride. That second word is more apt, the anion of acetic anhydride, or generally you can say it is a carbon anion. And here we have got CH3COOH. Now the CH3COOH, look at this, it is a weak acid, so always it exists in equilibrium, correct? And what you get here is CH3CO minus and H plus. Am I right? This CH3CO minus, it would again combine with Na plus and that would become CH3CONA. And there is always H plus. So this is all about H plus in the system. So that is, in the first step, the system is becoming acidic. That is what I wanted to say to you. In the first step itself, because of generation of CH3COOH, the system is becoming acidic. Acetate ion is combining with Na plus to give back the catalyst. So it's all about H plus. It's all about becoming acidic in the first step itself. I hope it is clear. So we got a carbon anion like this, right? Now let's go to step number 2. Step number 2. What do you think? The carbon anion will sit idle? Never. It will attack, right? So step number 2 is attack of carbon anion. Attack of carbon anion. Let's see what happens here. So carbon anion is this. This is the carbon anion we got. There is a negative charge over it. Now, where would it attack? Yes, there is aromatic aldehyde which is present as a reactant. Now there is a rift between carbon and oxygen. Both are of opposite nature. Carbon is electropositive, oxygen is electronegative. So there is always a pull of electron towards oxygen. Pull of electron cloud towards oxygen. So that would make it negative and this one, carbon, would become positive. Now what would happen? You guessed it right. The mechanism, name of the mechanism itself. Nucleophilic addition reaction takes place. So this is the main step. Nucleophilic addition reaction takes place and you get a compound like this. CH2CO minus because now it has completely gone to oxygen, the pair. So you get a compound like this in the second step. Am I right? Yes. Attack of carbon ion. Right? So you get the second compound. What has happened here is that an ion of acetic anhydride, it has attached, it has combined itself to the nucleophilic carbonyl carbon. And what you get is this compound. This is the nucleophilic addition. This is the main step of the whole reaction. Okay? Yes, fine. Now what happens? Let us rub this. Step number 3, protonation by acetic acid. Protonation by acetic acid. By acetic acid. Let us see what this step is about. Let's see what happens. I am going to write this here. Right, this is okay. Am I writing it correct? Just check. Okay, fine. Okay. So this is what I have written. Now I have shown to you, I have told to you that H plus is, it's all about H plus. Didn't I say that dialogue? In the first step, H plus is generated. Right? CH3COOH is generated as a simple molecule. It is generated as a simple product. And out of the CH3COOH, H plus comes out. CH3CO minus, some of it may become combined with Na plus and give back the catalyst. So it's all about H plus, didn't I tell you? So now this H plus will do all the things here. The H plus, it will combine with this, it will combine with the electron pair, and it will combine with the oxygen. So now what we get is this. So now we got this compound. This is the compound that we got now. Now, first step, second step, and the third step, they are similar to aldol condensation. First step, second step, and the third step, they are same to same. They are analogous to aldol condensation. So if you want to know, in aldol condensation also the same steps are followed. OH minus, it will take out a hydrogen from one of the aldehydes, from the aldehyde, and then the aldehyde, the anion, it will attack another aldehyde molecule in the same way, and in the third step protonation occurs in aldol condensation. So this till this, it is similar to aldol condensation. This till the third step. So 3 steps are similar to each other. So that makes it similar to aldol condensation. Now let us now go for the fourth step. If you want to know what is aldol condensation, please refer to my earlier video class on aldol condensation. Now let us go to the fourth step. Step number 4, internal proton transfer. Internal proton transfer and elimination of water. And elimination of water. Elimination of water. Let us see what we mean by this. So this is the molecule with us, correct? I am going to draw H here for this CH2 and OH, H, and this benzene ring. This is same, correct? Now this has a lone pair of electron, 2 lone pair. Now why would hydrogen be with carbon? There is no reason for it to be with carbon when a highly electronegative atom is nearby. This oxygen atom is so electronegative that it attracts the electron of hydrogen. It attracts hydrogen towards itself. So that's so electronegative. And now it has lone pair of electron also. So what hydrogen has, the hydrogen, what it sees as a better option is to go with this and get the lone pair. So when H goes with this and gets the lone pair, oxygen becomes positive. Now the only option for the oxygen to negate this positive sign is to take the lone pair of electron that it is sharing with carbon. Here it is positive. When H is joining with the lone pair of electron, it becomes positive. The only option for oxygen to negate its positive sign is to take the pair of electron that it shares with the carbon. So this will go here and positive sign will go. So now when this pair of electron goes here, this gets completely eliminated out as water molecule. H is already attached with oxygen, right? Now the pair of electron is there now with oxygen. So that pair of electron it need to give hydrogen. The lone pair of electron remains free. So it would become H2O. When it becomes H2O, dear students, this pair of electron has been left by hydrogen, it would come here. So now what we get is this CH3, C double bond O, O, C double bond O, CH double bond CH, and you get like this. And what is coming out? Water, H2O. So a lot of H2O is generated in the process and you get a compound like this. So this is the fourth step. Now let us go to step number 5. Rubbing it. Step number 5 is what is being generated in the fourth step as byproduct? Yes, water. So there is a lot of water now. So you can go for step number 5, hydrolysis by water. Hydrolysis by water. Okay, so you can write this here. CH3, C double bond O, O, C double bond O, CH double bond CH, and here you go a benzene ring. Shall I rub this one? Fine. Now it is added, hydrolyzed by water. HOH. Now there are two oxygen atoms here. They will try to pull the electron, correct, towards itself. So this side will become negative. Correct? This part of the molecule is negative and this part of the molecule is positive. Correct? So here also there is positive and negative. So the positive part will attach here and the negative part will attach here. Am I okay? Yeah. So now what happens? CH3COH, negative part attaches here and positive part attach here in this part. So you get CH3COH and you get the product for the reaction, alpha beta unsaturated aromatic acid. Alpha beta unsaturated aromatic acid, cinnamic acid, common name is cinnamic acid. So that is how you get cinnamic acid. It's a 5-step reaction, and so the mechanism is nucleophilic addition reaction. I hope you have understood the mechanism. Let us now go for the significance of cinnamic acid. So this is the cinnamic acid. Cinnamic acid itself is used as flavoring substance. It is used as flavoring substance, correct? And there are other compounds, derivatives of cinnamic acid. For example, ethyl cinnamate, methyl cinnamate, benzyl cinnamate. They are used in perfume industry. They are used in perfumery. Ethyl cinnamate, methyl cinnamate and benzyl cinnamate is used in perfume industry. It is used in perfume industry. Okay, so this is the first use of cinnamic acid. Okay, now it is used as a pharmaceutical agent. Cinnamic acid has anti-diabetic property. It is used as pharmaceutical agent. Cinnamic acid is also used as a precursor to aspartame. Aspartame. Aspartame is an artificial sweetener. Okay, so there are so many uses of cinnamic acid. Cinnamic acid itself is used as flavoring substance. It is used as pharmaceutical agent. It has anti-diabetic property. Ethyl cinnamate, methyl cinnamate, benzyl cinnamate is used in perfumery, and it is used as a precursor for artificial sweetener, which is aspartame. Aspartame. Okay, so this is the first use. So you need to make cinnamic acid. It is very valuable and it has got so many applications. You use to make cinnamic acid, and the way to make is by Perkin condensation. Now, from cinnamic acid you can make, you tell me what is it? If you want to know what actually it is, this one, please refer my video benzoin condensation. This is steel beam. This is steel beam. Steel beam, you can make steel beam from cinnamic acid. Now steel beam is a dye. It is optical brightener. Optical brightener means it has scintillating property. It can be used in laundry detergent. Okay, it produces a brightness in clothes. Okay, so steel beam is an optical brightener. It can be used in laundry detergent. Okay, it is also, some of the steel beams have dyeing property. They have dye. They are used as dyes also. And steel beam, from steel beam you can make a, look at this one, resveratrol. Sorry, resveratrol. Resveratrol. Resveratrol is found in the skin of grapes. It is an antioxidant. It prevents aging and other ailments related to free radicals. So this resveratrol is used in as nutraceutical. Okay, for well-being, for good health, it is used as a nutraceutical. So these many compounds you can make from one cinnamic acid, and to make cinnamic acid you need to go for Perkin condensation. So from cinnamic acid we can make steel beam, optical brightener used in laundry detergent. From steel beam you can make resveratrol, which is a nutraceutical and used for well-being. So these are the applications of cinnamic acid. And from cinnamic acid you can, for making cinnamic acid you need to go for Perkin condensation. Dear students, that completes the class. I hope you have understood and liked the class. If you have liked and understood, please do not forget to subscribe the channel. Do like it and share it with your friends. Thank you very much.